Hi everyone, my name is Widanaarta with student number 24055531081. In this video, I will explain book with title Manufacturing, Engineering and Technology in chapter 2 with title Mechanical Behavior, Testing and Manufacturing Properties of Materials. First, the introductions. The purpose of testing is to evaluate how material responds to force, deformation, and environmental factors. And the impact is to ensure chosen material withstand stress during production and service. In manufacturing operation, numerous parts and components are formed into different shapes by applying external force to the workpiece, typically by means of various tools and dies. Common examples of such operation are forging turbine discs, extruding various components of aluminum ladders, drawing wire for making nails, and rolling metal to make sheets for car bodies. And this we have the table 2.1 that has the materials in their alloy form as and relative mechanical properties of various materials at room temperature in decreasing order. In strength, we have glass fiber, carbon fibers, and Kevlar fibers. Hardness, we have diamond, cubic boronitride, and carbides. Toughness, we have ductile metals, reinforced plastic, thermoplastic, and wood. Stiffness, we have diamond, carbides, tungsten, and steel. And strength, we have reinforced plastic, titanium, steel, and aluminum. And in this introduction is implies why understanding the mechanical behavior of material is crucial in manufacturing. Testing reveals not just how strong a material, but also how it reacts under real-world conditions like stress, temperature, and fatigue. This knowledge helps engineers ensure that components will not fail unexpectedly during manufacturing or service. It provides a scientific foundation for decision making, enabling efficient design, safer product, and cost-effective production. The example is if a bike frame is made of the wrong material, it might bend or break while being used, even it seems strong at first. Next, we have the tension test. The tension test is the most common method for determining the mechanical properties of materials such as strength, ductility, toughness, elastic modulus, and strain hardening capability. The test method of tension test is the specimen is pulled anexially until fracture and producing stress strain data. So we have the stick and we pull it until we have the fracture in the middle of the stick. The key properties elastic modulus. The key properties is the elastic modulus, yield strength, ultimate tensile strength, and ductility and toughness. And the engineering relevance is provides data for design, safety, process limits, and quality assurance. These parameters define how a material will perform under different load conditions, guiding decision in manufacturing and design. By analyzing toughness and ductility, engineers can anticipate whether a material is suitable for forming, machining, or surface application. The example of tension test in real life is the fabric of a backpack strap must have tight tensile strength so it doesn't snap when carrying heavy books. Next is stress strain curves. As the load is increased, the specimen begins to undergo nonlinear elastic deformation at a stress called the proportional limit. At that point, the stress and strain are no longer proportional, as they were in the linear elastic region, but when unloaded, the specimen still returns to its original shape. Permanent or plastic deformation occurs when the yield stress Y of the material is reached. The yield stress and other properties of various metallic and non-metallic material also are given in Table 2.2. After that, the ductility is an important behavior observed during a tension test is ductility, the extent of plastic deformation that the material undergoes before fracture. There are two common measures of ductility. The first is the total elongation of the specimen given by elongation is equal LF minus L0 per L0 times 100. And the second measure of ductility is the reduction of area given by A0 minus AF per A0 times 100. Next is true stress and true strain. Engineering stress is based on the original cross-sectional area A0 of the specimen. However, the instantaneous cross-sectional area of the specimen becomes smaller as it elongates, just as the area of a rubber band does. Thus, engineering stress does not represent the actual stress to which the specimen is subjected. True stress is defined as the ratio of the load, P, to the actual cross-sectional area of the specimen. For true strain, first consider the elongation of the specimen is consisting of increments of instantaneous change in length. Then, using calculus, it can be shown that the true strain is calculated as E equals ln L per L0. Next is construction of stress-strain curves. The procedure of constructing an engineering stress-strain curve is to take the load elongation curve in figure 2.5, also figure 2.2, and then to divide the load by the original cross-sectional area A0 and the elongation by the original gauge length L0. Because A0 and L0 are constants, the engineering stress-strain curve obtained in figure 2.5b has the same shape as the load elongation curve in figure 2.5a. Next is the compression test. Many operations in manufacturing, particularly process such as forging, rolling, and extraction, are performed with the workpiece subjected to compressive stress. The compression test, in which the specimen is subjected to a compressive load, gives information that is useful for estimating force and power requirements in this process. This task is usually carried out by compressing a solid cylindrical specimen between two well-lubricated flat discs. The test of compression test is the specimen is compressed axially until a deformation or failure. And the observed behavior is materials may exhibit buckling, barreling, or crashing depending on ductility. And the limit is the friction at platen or the specimen interface can distort results. The compression test complements the tensile test by studying how materials react under compressive force. A specimen is compressed axially. An engineer observes whether it deforms plastically, buckles, or fractures. The example of compression test is The rubber in a car tire is tested under compression because it must handle the car's weight without collapsing. Next, we have torsion. The test method generally used to determine properties of materials in shear is the torsion test. In order to obtain an approximately uniform stress and strain distribution along the cross-section. This test usually performed on a thin tubular specimen. The torsion specimen usually has a reduced cross-section in order to confine the deformation to a narrow zone. The test principle is the cylindrical of specimen is twisted along its axis to measure shear stress strain, and the application is critical for shafts, gears, fasteners, and components under torsional loads. And the key parameter is modulus of rigidity, shear yield strength, and fracture behavior. The torsion test applies a twisting force to a cylindrical specimen, measuring its shear stress strain response. This test reveals the shear modulus, yield shear strength, and the nature of fracture under torsional loading. It is essential for evaluating components such as shaft, gears, and bolts that routinely experience tear in surface. And understanding torsional behavior ensures this element can transmit power safely and reliably in machinery and vehicles. The example of torsion is a screwdriver handle needs to resist torsion so it doesn't crack when you twist it hard to loosen a tight screw. Next is bending or flexure. A commonly used to test method for brittle materials is the bend or flexure test, which usually involves a specimen that has a rectangular cross-section and is supported. As shown in figure 2.11, the load is applied vertically at either 1 point or 2 point as a result. These tests are referred to as 3 point and 4 point bending respectively. The resulting data provides flexural strength and modulus, which are crucial for structural application. This information is applied in designing components like plates, beams, and other load-bearing structures where bending dominates performs. The example of bending is the plastic ruler students use in class may snap when bent too far, and that is the bending failure. Next is hardness. Hardness is commonly used property. It gives a general indication of the strength of the material and of its resistance to scratching and to wear. Hardness is usually defined as resistance to permanent indentation. Thus steel is harder than aluminum and aluminum is harder than lead. Hardness tests several Hardness tests several test methods using different indenter materials and shapes in figure 2.12 have been developed to measure the hardness of material. Commonly used hardness tests are described next. Hardness values are often correlated with tensile strength and provide insight into wear resistance. Because of their simplicity, hardness tests are widely used in manufacturing for quality control and process verification. The example of hardness is a smartphone screen is tested for hardness so it doesn't get scratched easily when kept in pocket with keys. Next, we have fatigue. Fatigue test methods involve testing specimens under various states of stress, usually in a combination of tension and bending. The test is carried out at various stress amplitudes the number of cycles it takes to cause total failure of the specimen or part is recorded. Stress amplitude is defined as the maximum stress in tension and compression to which the specimen is subjected. The property is crucial in designing parts that undergo continuous stress refill, such as aircraft wings, automobile components, and rotating shafts. Proper fatigue analysis helps avoid catastrophic failures in critical application. The example of fatigue is a paperclip bends back and forth a few times before breaking, and that's the fatigue failure. Next, we have creep. Creep is the permanent elongation of a component under a static load maintained for a period of time. This phenomenon occurs in metals and certain non-metallic materials such as thermoplastics and rubbers, and it can occur at any temperature. Lead, for example, creeps under a constant tensile load at room temperature. However, for metals and their alloys, creep of any significance occurs at elevated temperatures, beginning at about 200 Celsius or 400 degrees Fahrenheit for aluminum alloys and at about 1500 degrees Celsius for refractory alloys. The creep curve typically shows the three stages: primary, where the rate decreases; secondary, with a steady state strain rate; and tertiary, where damage accelerates to failure. Understanding creep is vital for ensuring long-term reliability and safety in high-temperature environments. The example of creep is a plastic gel left outside in the sun for years may start to sag and lose shape. Next, we have impact. In many manufacturing operations and machinery components, materials are subjected to impact or dynamic loading. For example, in high-speed metalworking operations such as heading to make bolt heads and it drop forging. A typical impact test consists of placing a notched specimen in an impact tester and breaking the specimen with a swinging pendulum. These tests provide insight into a material's toughness and its susceptibility to brittle fracture. A key outcome is identifying the ductile brittle transition temperature, which is particularly important for material used in cold environments. The example is a football helmet is tested for impact strength to make sure it protects the head when hit during a game. Next, we have failure and fracture of materials in manufacturing and in service. Failure is one of the most important aspects of material behavior because it directly influences the selection of a material for a particular application. The methods of manufacturing and the service life of the component. These are two general types of failure. First is fracture through either internal or external cracking. Fracture is further subclassified into two general categories, that's ductile and brittle, in figures 2.20 and figure 2.21. And the second is buckling as shown in figure 2.20. Other failure modes include buckling, fatigue cracking, and failures due to stress concentration. Understanding this mechanism is critical in preventing catastrophic breakdowns in manufactured products and ensuring long-term service reliability. The example of failure and fracture of materials in manufacturing and in service is chewing gum stretches a lot before breaking, is ductile, but a piece of chalk snaps suddenly brittle. Next, we have residual stress. When workpieces are subjected to plastic deformation that is not uniform throughout the part, they develop residual stress. These are stress that remain within a part after it has been formed and all the external forces are removed. Reduction and elimination of residual stress. Residual stress can be reduced or eliminated either by stress relief, annealing, or by a further deformation of the part, such as stretching it. Given sufficient time, residual stress may also diminish at room temperature. The time required for relaxation can be greatly reduced by raising the temperature of the workpiece. They can have both beneficial and detrimental effects. While compressive residual stress may improve fatigue resistance, tensile residual stress can cause dust distortion or even premature failure. Managing residual stress is a key aspect of ensuring product reliability in manufacturing. The example of residual stress is a glass cup may suddenly crack when hot water is poured in because of residual stress from the manufacturing process. Next, we have work, heat, and temperature. Almost all the mechanical work in plastic deformation is converted into heat. This conversion is not complete because a portion of this work is stored within the deformed material as elastic energy, known as a stored energy. It is generally 5 to 10% of the total energy input. In some alloys, however, it may be as high as 30%. In a sample frictionless deformation process, and assuming that work is completely converted into heat, the theoretical adiabatic temperature rise T is given by delta T is equal U per rho C. These effects are critical in manufacturing operation, where heat management determines not only material response, but also tool wear and energy efficiency. Balancing this factor ensures equality products and process stability. The example of work, heat, and temperature is when we cooking noodles, the stiff noodles becomes soft and flexible in hot water. That is the example of temperature effects of material. Well, that's all from me. Thank you for watching.